Assalamu alaikum and welcome Chem 30 to the one of the last topics in organic chemistry. And again, this topic is quite complex. There are several layers to it. What we're going to do is not show you all the individual layers, but really just give you a shortcut or a faster way and a simpler way of ranking the relative boiling points of organic compounds. Now, the real thing, like it was in earlier chemistry courses, that determines the relative boiling points or the ranks of boiling points between different organic compounds is the intermolecular forces. In the sense that the more intermolecular forces a compound has, the higher the boiling point is going to be because it has more forces to overcome. The more intermolecular forces a compound has, the closer those bonds are going to be together, and thus we need more energy to be able to split them apart. So what we're going to do in this video is give you the list in terms of functional groups, the list in order of the functional groups that have the greatest amount of intermolecular forces, and then the ones that have the least amount of intermolecular forces. And what we're really doing there is giving you the general functional groups that have the highest boiling points to the ones that have the lowest boiling points. The functional group with the highest amount of intermolecular forces are the carboxylic acids. They have a hydrogen bond from the hydroxyl that's bond to the at the end of the carbon in the compound, as well as an extra dipole moment from the double bond to the oxygen. So this dipole moment from the double bonded oxygen, along with the hydrogen bonding, create, well, in most cases, the greatest amount of intermolecular forces, and hence carboxylic acids are always going to have the highest boiling points. Then it's the alcohols, whereby they have the hydrogen bonding from the hydroxyl compound, but they don't have that extra dipole moment from the double bonded oxygen. So they tend to be second in terms of boiling points when it comes to organic compounds. Then it is the ester functional groups, and they do not have a hydrogen bond, so that makes them significantly less in terms of boiling points than the alcohols or the carboxylic acids, but they do have dipole moments that occur from the two oxygens that we find in their compounds, hence making them overall more polar than most organic compounds, and hence they tend to be the third highest compounds in terms of boiling points. Now, when it comes to the hydrocarbons like alkane, alkenes, and alkynes, the general rule is that alkenes have the lowest boiling points, followed by alkynes. And the reason why alkynes tend to have a higher boiling point than alkenes is because the triple bond actually ends up shortening the bonds, bringing the carbons closer together, which means it's slightly harder to pull them apart due to the increased magnetism. And then, of course, alkanes, which tend to be the more stable of all those three hydrocarbons, have the highest boiling point. So alkanes are the highest, then it's alkynes, and then it's alkenes. So out of all the organic compounds that we cover in Chem 30, alkenes have the lowest boiling points. Now, let's say we're comparing boiling points between like functional groups. So, for example, we're comparing three different carboxylic acids or three different alcohols, and within the alcohols we want to know which one has the higher boiling point. Well, if the functional groups are the same, then we resort to counting the number of carbons, and the general rule of thumb is that the higher the carbons, or the higher the number of carbons in a compound, the greater the boiling point. And the reverse is also true, whereby the less carbons a compound has within functional groups, the lower the boiling point it is with respect to the other compounds within that functional group. Okay, so when we look at the compounds that we've been given here, I've drawn them out. You don't really need to do this technically, but what I find is when you draw them out, it further reminds you of which functional groups each of the compounds belong to, and therefore it becomes easier to do the first two steps where you order your boiling points based on the functional groups. So when I look at the first two over here, these are alkanes. And so we're going to have to look a little bit further when we try to distinguish whether the propane or the methane has a higher boiling point. Now, here the double bond means that this is a propene, it's an alkene, and that is automatically going to have the lowest boiling point. So when we're listing our boiling points from, let's say, highest to lowest, we know that propene is going to be at the end. Now, in this case, we want you to list them from increasing boiling points, so from lowest to highest. So we know that right away, our propene is going to have the lowest. So I'm going to list that first. I would go propene, which has the lowest boiling point. And then it's going to be alkanes, which will be either methane or propane, but both of them will come after propene. Now, which one is going to come first, so the propane or the methane? Now, the suffix tells us that the propane and the methane are from the same functional group. So what we're going to have to do is, in order to distinguish between which one has a higher boiling point, we're going to count the number of carbons. When the functional groups are the same, then we count the number of carbons between them. And whichever one has more carbons, then that will have the higher boiling point. In this case, the methane has only one carbon, whereas the propane has 1, 2, 3. So then we can go ahead and say that, well, methane will come next, and then propane soon after that, or right after that. Now for the last two highest boiling points, we see that, again, based on the suffix, we have both alcohols or compounds of the same functional group. So once again, we're going to have to ask ourselves which one has more carbons. Whenever we're deciding of boiling points between two functional groups that are the same, you count the number of carbons. In this case, propane has 3 carbons. I can see 1, 2, 3 over here. And then ethanol has just 2 carbons over here. So that being said, that would mean that since ethanol has less carbons, it would have a lower boiling point than propan-2-ol. Let's take a look at another example. Okay, so much like the previous question, we're going to rank the following compounds, but this time it's going to be from highest boiling points to lowest boiling points. So we're going to start by stating the highest boiling points first. And the first place that we look, remember, is at the functional groups. And we prioritize the boiling points based on functional groups, meaning that some functional groups automatically have a higher boiling point than others. So we start there. So what I did is I redrew these. Now this is not necessary every single time, but what I find is that when we redraw these, the functional groups that are present in each of the compounds are made more apparent. So here I'm going to highlight all the common functional groups, and that's important because then we know that the strategy is a little different. We got to count the number of carbons. So we have the carboxylic acids over here. And those have the highest boiling point, so we know that we're going to label those first. So now here I place butanoic acid ahead of propanoic acid simply because it has a greater number of carbons. Remember that within functional groups, the greater number of the carbons, the higher the boiling point. But you prioritize functional groups first. Then, when we go down the list, there are no alcohols here, so we can skip that part. We do have an ester right over here, and so we're going to label that next as what comes after the butanoic acid and propanoic acid. Now, the reason why that is the case, we don't have to do that here in terms of Chem 30, but what you can do is really just memorize the general list. But the reason that in actual chemistry that is the case, that generally speaking esters have relatively higher boiling points, is because the double bonded oxygen here and even the oxygen bond here, but more or less this double bonded oxygen creates what we call a dipole moment and increases the polarity of the compound. So finally, with the major functional groups out of the way, we then have to decide between the alkyne and the alkane. And remember that between those hydrocarbons, the alkanes, alkenes, and alkynes, the alkenes have the lowest boiling point, then it's the alkynes, and then of course the alkane. And since they're considered different functional groups, the number of carbons don't matter in terms of priority. So butane has a higher boiling point than our propyne, simply because it's an alkane and those tend to be a lot more stable. So let's say from this question we want to rank the following compounds in terms of decreasing boiling points. Now decreasing really just means from highest to lowest. So we have an alcohol over here, and then we got two alkanes over here. Now we know that the alcohol is going to be first because alcohols have the second highest boiling points amongst all functional groups, and there is no carboxylic acid present, so we know that it'll be ethanol first, right? Or you could write the letter C. And then now between these two compounds, well, they're both alkanes. They both have the same number of carbons in the parent chain, right? They each have 5 over here. I'm highlighting the parent chains. But this one here has a branch right over here as indicated by the name. So what do we do when we have the same amount of parent carbons in the parent chain? Well, what we do is, if the number of carbons are the same, then we count the number of branches. And the rule that we're going to write here, and I'll write it to the side. And so the rule is that if the functional groups and the number of carbons are the same, much like these two alkanes over here, then as the number of branches increase, the boiling points decrease. And the reason for that is because as you add on branches, you get more frictional drag. But we don't have to know that in detail. What I want you to remember is that if the parent chain is the same in terms of functional group and number of carbons, then look at the branches. And the more branches a compound has, the lower the boiling point is going to be. So this compound over here, the pentane, has no branches, and this has one branch over here. So the order would be pentane would be the second highest, and then the lowest boiling point from these three compounds is going to be 2-methyl pentane. Now putting all the rules together, I want you to rank the compounds in terms of boiling points from highest to lowest. Pause the video, try them out, and then fast forward and see if you get the answers that we're getting.